Hello, this is Martin Horvath, and I'm recording this video for students of Biology 3510 to help with an overview of kinetics. And the goal here is to understand some of the schemes for enzyme kinetics, and we're going to begin with just simple chemical kinetic processes. Simplest one would be some chemical A turning into a product P. So one arrow, one chemical agent, and we can describe the intermediate on this path from the starting point A to the end point P. There exists some kind of intermediate, which we're going to call the transition state, and we often give this the symbol X double dagger. And this transition state is the way we make it is A acquires some energy necessary to reach this very unstable intermediate, and once it gets there, it has a possibility of becoming P. And with this scheme comes an energy diagram. Energies on the y-axis, and we call this the reaction coordinate. It's just a progress from A to P. A starts off here, and there's some activation energy barrier, an energy that we have to acquire. It's called delta G double dagger. And up here at the very tippy top is this transition state. And the likelihood of getting to the transition state is related to the exponent of this activation energy barrier, and so this is really, even small differences in this energy can have a big impact on the rate. We can also write that the rate, meaning how quickly product is accumulating, that's going to be proportional to the amount of our starting material. So some rate constant. And because this only involves one molecule, we call this, this is a unimolecular rate constant. Or it's also referred to as first order. And that means it will have units of reciprocal time, often reciprocal seconds. A slightly more complicated rate process might involve making the transition state from two things. So on the way to making product, we again encounter a transition state, but now we require A and B to find each other, and then also acquire activation, get to this activation barrier. And in that case, the rate is more complicated. There's still a rate constant, but now it depends on both the concentration of A and on the concentration of B. And we call this a bimolecular process. It's second order, and therefore it's going to have units of reciprocal concentration, reciprocal time. So for example, reciprocal molar, reciprocal seconds. And if we were to plot how the rate depends on each of these agents, it would look like this. The rate as a function of A, you'd get data points that fall in a line, and the slope here is this rate constant K. And for the second example, it looks similar, except that in addition to being linearly dependent on the concentration of A, it also, the slope increases as we add more B. So more concentration of B. And in this situation, each of the data that are collected for any given concentration of B, it appears to be first order, and that's referred to as pseudo first order, meaning like it looks like it's first order, but it's truly second order because we can increase the rate when we add more B. All right, and this is all build up to understanding what's happening when enzyme and substrate find each other, and we consider this to be a reversible process. They make the enzyme substrate complex, and then that enzyme substrate complex can go on to make the product and regenerate the catalyst, the enzyme. And en route, again, we form the transition state, but now the transition state is happening in the active site of the enzyme. And so here we have a bimolecular process, enzyme and substrate finding each other, similar to A and B finding each other. And we also have a unimolecular process, the enzyme substrate complex becoming product. So it resembles, in some situations, the unimolecular example, and in other conditions, it'll obey patterns consistent with a bimolecular situation. And here, the rate, as described by Michaelis and Menton, is going to be equal to some rate constant. This time, we're going to give this the name kcat, times the concentration of enzyme times the concentration of substrate, divided by the sum of two terms, Km plus the concentration of substrate. So this is more complicated than the other ones, and the graph, if we graph this is going to look like, it's going to look very familiar to us. It's going to look like a saturation curve, similar to the ones we've been studying for myoglobin or general receptor ligand interactions. So here's the concentration of substrate. So what we want to do is try to explain why the curve looks like this, with hyperbolic and with a limit. This is the maximal rate. We give it a name called Vmax. And it's not often included in textbooks, but we should also consider that this is the rate also depends on the concentration of enzyme. And here we expect a linear trend, and you can always make the reaction go faster by adding more enzyme, but under some conditions the reaction stops getting faster when we add more substrate. And that this idea of saturation is embodied here. There's a limiting number of active sites where the chemistry can happen, and once we've saturated all of the enzyme active sites with substrate, now we cannot go any faster. At this limit, we say that it's zero order. It no longer depends on this concentration of substrate. And then here, in this region, it appears to go up nearly in proportion to how much substrate we're adding. And that's similar to this pseudo first order, because if we added more enzyme, both the Vmax and the slope of this beginning portion would increase, as indicated by this second plot. Okay, so I want to wrap up by talking about what each of these kinetic constants refers to in terms of molecules. Kcat is this arrow here. It is like that first order unimolecular process. Once we've made the enzyme substrate complex, it is describing how quickly can we make the product. And one way to think about it, if this is very fast, then the chemistry is easy. So it's a reflection of how difficult the chemistry is. Hydration of carbon dioxide or dehydration of bicarbonate is very easy. So this will be fast if the chemistry is easy, and it'll be a lower number if the chemistry is difficult. So this is a reflection of how easy it is the chemistry. Another constant that's in this equation is the Michaelis-Menten constant, and this is the amount of substrate that's needed to reach half saturation of the active sites. So when we're at this balance point, the 50, we're familiar with this balance point with myoglobin. We call it the P50 value. When we're talking about acid dissociation constants, we refer to it by its negative log 10 of the Ka, so pKa. And the same idea here, but it's a little different than an equilibrium constant in that we can remove or vacate the enzyme active site in two ways, either by dissociating the substrate or by doing the chemistry and getting to the product. So Km is a mixture of all of these arrows. So it's a little different than a dissociation constant, but it's still true that by definition, it's the amount of substrate needed to get to half saturation and therefore you'll experience half of the maximal rate. So how difficult to saturate the enzyme. And then we also pay attention to Kcat over Km. These two parameters together, these are a reflection of the limiting case when we have very little substrate, where we're no longer limited by chemistry, we're limited by enzyme and substrate finding each other. This is the rate at which they can find each other is described by Kcat over Km. And you can think of this as like enzyme and substrate finding each other. And in solution, in a search that's random in 3 dimensions, this has a limit of about 10 to the 9 reciprocal molar reciprocal seconds. We don't expect anything to go faster than that, but some enzymes do figure out a way to be faster, and those enzymes that reach this upper speed limit or exceed it, we refer to those as perfect enzymes. They're doing their job as efficiently as possible, only limited by how their strategy by which they find each other. And for an enzyme like MUT-Y, that search is no longer always 3-dimensional. It sometimes is a 1-dimensional scan of the DNA, and that's much more efficient. And that explains why MUT-Y can achieve this very high Kcat over Km performance rating.